So again, this is part of the bird's eye view. And I want to talk about hardware. All right. So one thing to talk about is displays. So again, we've talked about screens for, I should say visual. So examples of visual. So we could have screens like maybe going back to cathode ray tube monitors, right? I think you're old enough to remember those at least, right? LCDs, plasmas, I don't know, organic LEDs and so forth. And maybe you might want to involve lenses in some kind of optical system if you're making a head mounted display out of these. You can get a little more exotic and do virtual retina display. There's a lot of work on this going on in industry, a lot of it let's say behind closed doors. So a lot of research, a lot of prototypes being developed with virtual retinal displays. Essentially just take a tiny projector and just project images directly onto your retina, but of course they're still going through the lens of the eye. So it's not exactly the same as you would think, but at least you're not trying to just simply look at some pixels and deal with whatever the relationship is between that and how it falls onto the retina. You're directly considering what information should be presented to the retina. So that's one possibility. There's also an interesting and exotic family of displays called light field displays. You can research these on your own, light field displays. I will not cover these things. In this case, rather than presenting the information on as a two-dimensional projection, they try to capture the entire field of light within a three-dimensional region. And this is very helpful so that when you rotate your head and your eyes are translating through space, or you move your head around inside of a cubic, let's say, volume, then you can adjust the information that's actually presented to your retina in terms of where your position and orientation are in that space. So you capture the entire light field using something like say a planoptic camera array or some other kind of device. It's also very difficult to do, and then present the entire information in some way so that you can in real time take into account these small motions and present the entire light field. So that's another possibility. And I guess somewhere in here I should have mentioned let's say projectors. I'll put it up here by screens. In fact, I probably should have put it first. We've had movie projectors for a long time, going all the way back to the beginning of film, like the train pulling into the station from 1895. So maybe projectors should even be first there. Right. For audio, so that's visual. Just think about displays again. So audio, speakers, or earphones, which are small speakers. You can fool your audio sense by bone conduction as well, right? Some bone conduction audio techniques. Touch. So there are what are called haptic devices. And you know, I won't have time to cover these in the class, but a couple of general categories which are worth considering about is cutaneous versus kinesthesia. It's a nice way to divide these up. An example of the first one is maybe I just get some kind of vibration as a kind of feedback, right? A rumble pack in a game controller would be an example of that. Or maybe my motions actually get blocked. I feel a resistant force. There may be a robot on the other end pushing back at me, right, and providing the right force so that it feels like I'm touching a wall. I keep getting stopped every time I put my hand out, right, but maybe a robot hand that's touching mine, let's say. So that would be an example of kinesthesia. So, so you can provide this kind of feedback as well. And as far as going into smell or taste or vestibular stimulation, I guess I won't include too many examples of that, but there certainly is ongoing research on those as well, providing the right chemical feedback to trick your sense of smell or taste. And there's electrical stimulation of the vestibular organ that's possible, but I don't recommend trying it. So it's very painful from what I hear. All right. Other hardware you might think about inside of hardware. Other hardware, of course, we have computers on use, and we have graphics processing units. Let me just kind of, just to kind of list off everything. Computers and GPUs inside of there. So let's say CPUs and GPUs. And I should also say that there are inputs. And in this case, maybe something like a game controller. Keyboard. We talked about data gloves, been around for a long time. So it's a lot of interesting research and development going on this part, by the way. Input devices for virtual reality. There's a lot of open work to be done there, because once you put on a virtual reality headset, it's like a blindfold, and probably the last thing you want to be doing is just feeling around for the keyboard, right? So how can you do things like suppose you want to sit and write software inside of virtual reality. You just want that to become your desktop, right? So how do you do that? How do you enter data fast enough and in a comfortable way and interact with your environment? Is it going to be a keyboard and mouse, or is it going to be something else? One more bit I want to say about hardware is, what do we use for tracking? So tracking is going to become very important, as I talked about in the case of a head mounted display. When you turn your head, you have to get the visual information to update correctly so that it really looks like the virtual world, or this alternate world, is responding appropriately to fool your brain. So tracking becomes very important, and the more portable the device gets, or the closer it gets to the actual sense organ, the more kinds of tracking you need. If I'm in a cave system, I can see my entire body as I walk around, right? If I put on a virtual reality headset and look down, I don't see my body. So I have to invent a body. How do I do that? Well, I can track my body and then bring that into virtual reality, but that's a lot of work. It's very challenging. It's reasonable as a class project, but it's very hard to make it 100% reliable and accurate. So, so these things don't work very well. They look great, they make great demos, but very, very hard to do that. You could put on a motion capture suit, a full body suit with markers, gets a lot better then. But if you're going to do that much work, why not just build a cave system? So it's a very interesting kind of problem. So I want to talk about tracking, and this will finish off the hardware. Where's my chalk? Okay, let's see. I'm leaving it there. All right. Tracking. So you call this tracking, or estimation, or filtering. So people in electrical engineering will tend to use words more like that. One of the most useful components is the inertial measurement unit. People call it IMU. So IMUs have been around for a long time. They were originally designed for navigation, especially useful in aircraft and spacecraft. So if you've flown on airplanes before, almost certainly there was an IMU on board, usually a rather large mechanical device. So the purpose is to provide orientation estimation. So these are used for orientation, or rotation if you want. estimation. And so that's their main design. What it measures is 3D angular velocity and 3D linear acceleration. So the angular velocity measuring part is usually called a gyroscope. Sometimes people refer to the entire inertial measurement unit as a gyroscope. I think that's not quite right. And this part is called appropriately an accelerometer. So this measures linear acceleration, but it's also measuring acceleration due to gravity, because there's no way to really separate true linear acceleration with respect to the fixed Earth and gravity in a natural way. There's no natural way to separate that. You're always measuring the vector sum of those two. It's as if we're all on a rocket ship right now accelerating that way at 9.81 meters per second squared, which is why we're all stuck to the floor, right. So that acceleration is always being measured as well. All right, so we have the inertial measurement unit. The interesting thing that's happened in this technology is that our smartphones have IMUs inside, mainly so that you can play these apps where there's a ball rolling around, or I guess it's designed so that it tells you whether or not the screen needs to be reoriented, which frequently seems to fail, and it very often fails because you're moving while orienting, and this linear acceleration of the device is getting confused with gravity. There's all kinds of issues like that. But these started appearing in smartphones. They became very, very cheap, mass produced on the order of hundreds of millions, and now you can just take those and put them inside of virtual reality headsets, and you have an IMU to use, and it doesn't cost very much money at all, right. So it can be mass produced. You can also put them inside of earphones as well. So this is great. You can stick them on robots. You can put them all over the place to estimate orientation. So that's one of the greatest enabling technologies. And one thing that's very closely related to the inertial measurement unit and is sometimes considered a part of it is magnetometer, which measures magnetic fields, 3D magnetic field. You can sort of think of it as a compass, but it's not exactly a compass. It's going to measure the vector sum of the Earth's magnetic field and whatever other magnetic fields are around in the building, let's say, or on the circuit board that contains the magnetometer. So it's just generally measuring magnetic fields. That's also used to provide orientation information. Other hardware, cameras have become quite useful. You'll notice on the DK2, Oculus DK2, used in the lab, there's a camera. So that's being used as part of the tracking system as well. And when you use cameras, there's generally two different kinds of ways of doing tracking. The names are inside out and outside in. Honestly, I got these. I found it very confusing. It took me at least a few weeks to keep them straight. So I don't know, but these are the terms that are used. So in the inside out case, this is a top down view. You're wearing a headset and there's a camera on it here, let's say, and then there are some markers in the physical world. I'll draw markers as pluses, features or markers. So they see these markers, and so based on how these markers appear to the camera that's fixed to the headset, you can figure out where you're at. These markers could be engineered, or it could be using natural features from the environment. If you engineer them yourself, then you get very accurate, very reliable performance. If you just extract them automatically, it makes a fun project, but it's an interesting demo maybe, but it's very hard to get perfect accuracy and reliability, or very, very high accuracy and reliability like this. But nevertheless, either way, this is inside out. The other way is outside in, which is what happens in this Oculus Rift DK2 case. Again, you have the head looking straight down. You have the headset on. And then there's the camera out here looking. And so these features, draw them in another color here so we see them, are on the headset itself. In the case of Oculus Rift DK2 that you'll use in the lab, these are infrared LEDs that are embedded inside of the headset. The plastic is infrared transparent, but in the visible spectrum it looks black, so you can't see the LEDs, but they're inside of there. So in this case it has markers. So this is outside in. In other words, the camera is outside looking inward, and in this case the camera is inside the headset looking outward. So these are ways to use cameras, and we can talk about the technology of doing this tracking later in the course. I will spend some time on that. And of course you can add to the cameras depth information. So you can have what are called you know, including depth, like information provided by the Kinect using current technology to give you what are called RGBD sensors, right, giving you color and distance information. So there's cameras for that, and those are going to be very important in the coming few years. As the cost of those goes down, the reliability goes up, the accuracy improves. There's going to be more and more technologies that use depth cameras for various kinds of tracking. So you put all this together. There's also more methods that use electromagnetic fields or magnetic fields that are generated by a base station, and you can do tracking that way. One thing to think about throughout these tracking technologies is, what do you need to track? Track your head, track your eyes. You want to track your entire body? Do you want to track an entire room full of people? Right, all kinds of things you think you want to do. And you don't necessarily have to do that. For example, I'm giving a lecture today, and I can only look at one of you at a time, right? If we were all in virtual reality doing this lecture, I could be looking at all of you at the same time. Like each one of you would see me looking directly at you, right? So you don't need to have my head tracked perfectly. I need to have my head tracked perfectly, I guess, to have the display work correctly. But I don't need to have where my eyes are looking tracked perfectly in terms of what you see. I could just make it so that I'm always looking at you, so that you're always paying attention to me. And you get the feeling individually that you're being looked at. But really, I can't possibly be doing that. So there's cases where you do not want to provide the exact information that's going on in the real world. So you really have to think about these things carefully. And there's always a cost involved, and accuracy issues and comfort issues. Again, if you're tracking the body and it looks like my arm keeps breaking and bending in a backward direction, that's not comfortable, right? It's torture of some kind, right? So if your system's not working reliably, it's probably not worth doing, or you have to assess, is it really necessary? If it is, then throw all the resources you have into it and make it work. But it might not be. Even though it might look cool, it might not be necessary. All right, so that finishes the hardware part. I want to talk about the bird's eye view of the software. Are there any questions about hardware? Again, this is a very high level overview. I'm going to go into more details of these things. In fact, I'm covering the fundamentals. So by giving these examples, you'll be able to see more of why I'm jumping into various fundamentals.